like to thank the organizers for this nice school, and also speakers for the talks and lectures. I've learned quite a lot here. So now I'm going to talk about more or less the last slides of Andrei Marshakov's talk, and I will try to explain how can one understand these formulas for the general solution of some Q-difference system, or it can be applied also to other examples of Penrose equations or Q-Penrose equations. So I will try to explain it by simplification. In a sense, I want to take the formula for solution of the non-autonomous equation just like something given from above, and then show how to use it, how to take autonomous limit, and how to compare it with something much more simple, which can be written in terms of theta functions, but not in terms of Nekrasov functions. So let me start from the non-autonomous equation, and let me first write it down. So I will work with this Y and K system. Which was on the last slides of Marshakov's talk. Well, this system can be written in the bilinear form as an equation for tau functions. So here it is. Andrei already wrote that solution to this bilinear equation can be written as a discrete Fourier transformation of Nekrasov partition function. So here is this formula. So it depends on z, which is at the same time coupling constant and evolution time of the non-autonomous system. It depends also on vacuum expectation values of scalar field in the supersymmetric gauge theory, and it also depends on the Fourier transformation parameter, which is in some sense dual to the to this vacuum expectation value. So the formula has this form. So it's sum over. For simplicity, I can say that the sum is just over some lattice of rank n-1. So here is this Fourier prefactor. With shift by by the vector which should be identified with the first fundamental weight of the SLN root lattice. Maybe it's better to denote it Qn, but say that it's isomorphic just to integer lattice Zn minus 1, because we don't care much about the scalar product in this lattice. Okay, so the formula is the following. Here is this Fourier prefactor, and parameter S enters only here. And here is a Nekrasov partition function. Okay, so I can remind you what is the approximate form of this Nekrasov partition function. Though we will not need this, just to remember what it is. So as series in Z, it's some fractional power which can be written in this form. Times some structure constant depending on U. Times big sum over n tuple of Young diagrams, lambda 1 and so on, lambda n. So it's some serious expression, but what we will use is not this explicit form. We will use instead the Seiberg-Witten limit of this expression, which will be described by Seiberg-Witten prepotential. Yeah. So I will continue with this a little bit later. Before that, I would like to tell a little bit more about this equation itself. So to understand what it is, I think it's better to look at its 4D limit. So how to take this limit? We have to send Q to 1 in the following way. So it's 4D limit, and let's denote the radius of this fifth dimension, which we are trying to reduce by r and send r to 0. So in this case, we say that Q is an exponent of r, and Z, the coupling constant, is r to the power 2n times Z for D. If we do this, then we see that the equation transforms to the following thing. We have so we transform it a little bit and get something like this. Okay, so times the same factor with opposite shift. So now what we see in the left hand side in the limit r goes to 0, it's second Herta derivative divided by tau j squared, but we can write it explicitly as a logarithmic derivative over the log of z for d. So it's d squared log z for d of log of tau j equals to the ratio of the tau functions. Sorry, I forgot this tau j squared. Okay, so here's this equation which can be something known for some people, but to make it absolutely recognizable, we can. Sorry, I forgot this non-autonomous factor. To make it absolutely recognizable, we can make one more change of variables by denoting first this combination by r, and then this combination by phi. In this way, we get a radial Toda equation, which has this form. Okay, so as it was promised by Andrei Mashkov, for example, you see that dependence on k disappears in this limit, so all these equations go to the same radial Toda equation, and the reason is that there is no Chern-Simons term in 4 dimensions. So, and also, it also tells us that if we want to solve a radial Toda equation, we can take this 5D solution and take this limit at the level of solution. It's quite easy to do. We have, as always, replace all trigonometric monomials with rational monomials. So it's kind of a trivial procedure. But now I want to go back to the initial topic of my talk and consider the autonomous limit of this system. This limit is, in some sense, it looks a little bit similar. Because in this limit we also send q to 1. Sorry. Epsilon goes to, we take some parameter which will control this limit. Call it epsilon and send it to 0. Then q should be e to the power epsilon. But that's all. We do not take a limit for z. We just keep z the same. But now there is a new phenomenon. So now we see that when we perform this shift by Q, that shifts just a little bit. It's multiplied by e to the power epsilon. But this z is present in the equation. Looking here, we see that from one side there is some dynamics, there are some tau functions in different points. But from the other side, the equation itself doesn't change a lot. So it should tell us that the good formalism to describe the system is to introduce two sets of variables, fast variables and slow variables. Fast variables are this n and also j, because they describe some dynamics. So tau functions for different j's and for different n's can be quite different, though a value of variable z itself is almost the same. Okay. So maybe, I don't know, is it clear what I'm trying to say, but I hope it will become clear soon. So, so here we have to introduce some list of fast variables, which is just a, n, which is here, and j. And the slow variables I will also introduce the exponential parameterization for use. And also it will become clear a little bit later. We should send this parameters of Fourier transformation to infinity. Si should be of order eta I over epsilon. Yes. So slow variables are they're not AI and eta I. So
if n is integral number,
yes, there are two integer numbers.
So why should we put z is equal to 0 times e to the
no, but it's by definition. In our equation, we have sorry, n is not exactly integer number. It can have such shifts by k over n. This precise statement. Oh, we just look at our equation. We see that only possible shifts of z are q to the power k over n and q. So to solve this equation as some equation with the initial conditions, it's enough to consider only this lattice. So and now I'm. Is it okay? Now I'm saying the following. We have this equation, and when we change z, for example, we shift it like 1,000 times, but if epsilon is small enough, then this z in the equation doesn't change at all. So we can consider this equation as autonomous equation by at quite big periods of time. So if epsilon goes to 0, then evolution of z becomes very, very small. So we can solve this equation as autonomous for some fixed value of z, and then consider dynamics of this slow variables. So this fast dynamics.
What is it? Should we see that instead of non-autonomous time z, you discrete time and small? Yes.
Yes, but actually this time was discrete from the very beginning. It was just convenient to write it in this way. This is the only possible. So that lives on almost on the integer lattice. Is it okay? Okay. So now let us maybe it was better to write this from the very beginning. So our equation now becomes of this form. Sorry. Okay, so this is what happens with the equation. So now we can say that we can neglect the fact that this prefactor changes and solve it as an autonomous equation. So it's one way, and then we can turn on some perturbation and consider the dynamics in this z0. And this was, for example, what Kachver did for isomonodromic deformations. It's exactly what happens if we put epsilon in front of derivative in the Schrödinger system. So, but here I want to say that it's much easier when we already have the general solution of the non-autonomous system. So it's much easier to take a limit of the solution other than of equation. Oh no, not of equation, but of. But it's easier to take a limit of a known solution rather than to compute its expansion order by order. Okay, so how to take this limit? Let me write this formula. Keep in mind the behavior of Nekrasov partition function in the limit q to 1. So it is known maybe from Nekrasov or maybe from some other sources that typical behavior of this Nekrasov partition function in this limit when epsilon goes to 0 and all other variables are the same so is the following. So if you it's e to the power 1 over epsilon squared times prepotential. Let me put here e to the power a. It's prepotential depending on a and depending on z, plus something of order 1. But we will not care about even this first correction. So when we see something like this, it's quite natural to try to compute the sum as we usually compute integrals of the functions of this form. It should be computed by a kind of saddle point computation. But the problem is that sum is not an integral, and we cannot approximate it by the integral in a naive way. So let me first write what we have, or maybe. No, first I would like to comment also on this phenomena. So absolutely the same phenomena occurs in the matrix models, but in that case we have n squared instead of 1 over epsilon squared, and it leads to some problems sometimes, because if we have a solution with several cuts, then we have extra variables parameterized in this solution, and these variables are filling fractions of this cuts. So if we naively take a partition function, then we expect that it should be something of order e to the power n squared times planar partition function. And if we suppose that the general expansion has this form, you can have some strange problems and contradictions, and it was work by Bernard, David, and Einar. Where they found that the resolution of all these problems is the following: that if we compute the matrix model partition function with fixed filling fractions, that then it's true that it has a genus expansion, but in the actual matrix integral, we have to sum over all filling fractions. We have to allow eigenvalues to jump from one fraction to the other one, and this sum is almost the same as this sum in the isomonodromic tau function. And what they got the theta function as a result of this summation. So if we have a theta function, then it's definitely clear that it doesn't have genus expansion because it oscillates, and it resolved some of the contradictions. So, but there it looked like some bug, but in our case it will be definitely a feature, because this theta function will be theta function describing an autonomous solution. Yes, so let me write down this Fourier series. So the formula for tau Jn is the same as on that blackboard, but in a little bit different notation. So it's the sum over lambda this Fourier prefactor with a factor 1 over epsilon So now we use this knowledge about asymptotic behavior of Nekrasov partition function and write it in this way. A plus plus epsilon lambda, because there was a shift by q. So it's plus some small number, plus epsilon omega 1 z0 times e to the power n epsilon. So here that's all, but plus all of 1. Okay, so once we have this expression, we want to apply something like saddle point computation, as I already told. So how should one do this? We can try to plot this function as a function of lambda. Let's suppose that this lambda is one-dimensional, because otherwise it's maybe impossible to draw. So let's draw some schematic plot of this summand as a function of lambda. And we would like to plot maybe absolute value of this. So a typical behavior should look in the following way. It should be some very sharp peak around lambda equals to some lambda star, which is an integer number. Or integer vector. So this is typically expected behavior. So we just need to compute the maximum of to find the maximum of the real part of this argument of exponential. So this lambda star should be found from the equation that derivative over a of the real part of the summand. Maybe derivative over lambda, better to say, of this e to the power 1 over epsilon eta oh, sorry. Maybe it's even better to write it in this way. Of eta plus d f over dA. Sorry. It should be equal to 0. So it's different from the standard saddle point computation, where we would like to deform our contour in a way to get through the real saddle point, because the saddle point is somewhere in the complex domain. It's hard to draw it in this real picture, but the actual saddle point is somewhere in the complex domain. So in this case, we cannot go there because we have a summation over this lattice on the real line. So the only thing that we can do is to solve this equation and to find the point in which absolute value is maximal. So if we draw the picture for example, for this prepotential itself for the real part of the prepotential, or maybe for the real part of the summand. Then we will have some oscillations of with a growing amplitude. But so it will be kind of maximal argument, but not a stationary phase. So we will I need to take some sum over nearby values of lambda and see what we get. Yeah. So what do we have now? We have chosen some point lambda star, and say that it will be some slow variable in a sense that although this equation depends on it might depend on the fast variables, but we are forgetting about this dependence. So for example, if we shift z a little bit, for example, by 5 epsilons, and found that the position of the maximum shifted somewhere, we don't shift it, we just work all the time with the same lambda star. So this lambda star will not depend on n and j. So we add this to the list of slow variables. So this lambda star is just a function of z0, eta and a. We will not find the best point for each tau function tau j, and we just take one, and we are happy even with this expansion around a single point, because epsilon goes to 0, so even some finite shift will not break this expansion, because it's finite shift. Okay, so let me.
Just to follow. What are your now assumptions of your variables? Epsilon is real.
I am considering it as real, but we can choose it imaginary as well. So somewhere should be not the real part of some function, but real part of function times something.
Just to follow. So anything else is complex, but you have assumption on epsilon. No, some numbers are integer.
N and j are integer, or something fractional integer.
Yes, integer and epsilon is real, and all slow variables are complex.
Yes, but we can also take epsilon to be complex. It
Need to change this.
yes. So there should, yes, there should be some argument of epsilon, but I have not thought about this. So let us work with what we already have. Yes.
Do you expand exponential of n epsilon inside F? Do you expand exponential of n epsilon inside F? Z0 times e to the n epsilon? Yes.
I have not yet, but I will.
Because in this formula it seems that there must be contribution for this.
No, but this is exactly what I'm saying. We are forgetting about dependence of these variables on n and j, and we take just some rough estimation of this position of the maximum. It's all the same for all n's and j's. Because it's integer number, it will not be good if we change it for different tau functions. So it's not the true maximum for all n and j's, but it's fine. Anyway, so we just need some reference point to start our expansion. Okay, so you can think that it's for j equals to 0, n equals to 0.
So you say that there are corrections for the solution, but they are like we will take them into account perturbatively by summation.
Yes. So, yes. Because otherwise it will be impossible to work with this, because this is an integer number and it can jump at random time, because at some moment the value in this point becomes less than the value in this point, and we don't want to think about this at all. Okay, so this expansion takes this form. So we have to expand this potential to the second order and get something like this: sum of lambda e to the power half of lambda times second derivative Okay, so it's a second order of expansion. It's a first order of expansion, and here we will also have some non-interesting but important factors, which are linear and quadratic in J and N. Some linear plus quadratic outside this summation. And times overall factor, which is the value in this kind of saddle point. It's 1 over epsilon squared times f, and plus eta times something. Okay, so what we are getting here is the formula for the theta function, with period matrix given by the second derivative of the perpotential, as it should be. So it's something similar times the theta function of this argument. 1 over epsilon eta plus df over dA star plus j omega 1. So it looks like a typical solution of the integrable system, but there is still something to compute. Namely, we have to find explicitly the dependence on the other first variable on n. So here we have a potential depending on A and Z. So we have to expand it a little bit more. So maybe I'll move to this blackboard. So do I have 10 minutes? Oh.
Yeah, sure. We started a little bit late, so I'll have questions.
Okay. Okay. So here we have this term with explicit dependence on n. So we have df over dA dependent on A and z naught times e to the power n epsilon. So it equals to df over dA with just A, maybe better call it A star. Z naught plus epsilon times second derivative. D log Z naught times n. So and it's exactly of the same of that order of magnitude which we need. Oh, sorry, I forgot here times epsilon. So the formula for the tau function has this form after all these computations. Is some simple prefactor times times tau of some initial point which depends only on slow variables. Plus two shifts corresponding to the fast variables. First shift is this cyclic shift of the number of the tau function, and the other shift is this shift coming from n. Okay, so here is this formula. So, Now I would like to explain what is the relation of this formula to the picture from the Krachyvar stock, and also I want to explain how to see that a solution of this autonomous bilinear relation should be found in this form. So you see here the theta function, and you see the period matrix of Seiberg-Witten curve. So it's time to introduce this Seiberg-Witten curve and to say who is who there. So you have already seen the Seiberg-Witten curve for non-relativistic to the chain, but here I want to but probably you have seen even this curve. I don't remember, but I will write an equation. So it's a curve which corresponds to this Newton polygon. Also, lambda inverse, which is here, plus mu to the power n minus k lambda, which is here, plus mu to the power n plus C0 plus and so on plus C n minus 1 mu to the power n minus 1. And here is C0, and here are all other variables. Okay, so first we have this curve, but to define the Seiberg-Witten prepotential, we have to write down also the Seiberg-Witten differential, and it has this form. It's a relativistic system, so it should be always log lambda times d log mu. Maybe I will write d log mu as d mu over mu. And in the previous talk, there was not log lambda, but just some variable times w over w. So it's a relativization of that case. Okay, so we have this curve, we have this differential, and now what is the Seiberg-Witten system on this case? What is it? So it's the same as always. So we are saying that there are n minus 1 periods of this differential integrals over a cycles, and this integral is equal to a i's, to the vacuum expectation values. So here we have some dependence of these C variables, C1 and so on, C n minus 1. And here we have vector expectation values parameterized in terms of coefficients of the curve. So we can use these equations to find C's as functions of A's. So the second set of equations define Seiberg-Witten prepotential. So, and now we can exploit these equations to understand what is written here. So, Andrei already told that second derivative of f is a period matrix. So, to get this and to get other formulas, we have to just differentiate these equations. For example, if we differentiate the first equation, we see that the integral of ds over daj over cycle ai equals to delta ij. And if we know that derivative of ds over some parameters in these points give holomorphic differentials, we can easily check this. So if we know this, that then we immediately conclude that ds over d ai equals to holomorphic differential d omega I. But also if you want to take the derivative over log z, we can do absolutely the same. We know that ds over d log z equals integral over a cycles equals to 0. So it tells us that df over d log z is some normalized differential, and to understand what is this differential, you have to look at his singularities. So the only variable which can depend on z is this c0, and we can find this dependence. It will be z0 to some power, but analyzing this derivative, that we see that there is meromorphic differential with poles in these points. So any boundary of the Newton polygon corresponds to some point in the infinity, because we can solve this equation in the limit where there are only two monomials, this one and this one, or this one and this one. So there are 2 points, so let's call them x and v. Maybe this is x. So from this explicit computation, we conclude that this ds over or ds, sorry. Or d log z is a meromorphic differential with some coefficient d omega of x v. So what is the question? We want to find the second derivative of the prepotential. To do this, we take the second equation and write it explicitly, that df over d a and d log z equals to the integral of over b cycles of d omega x and v. But we know by Riemann bilinear relation that this integral equals to the difference of the abelian maps of these 2 points. Minus a of v. So what is written here actually, that tau function of Jn equals to something times theta function of some point in the Jacobian plus some abelian map of divisors, how to say it? So let us say that we have one divisor multiplied by j plus another divisor multiplied by n. So and so it's exactly Kirchhoff's picture that we have some point on the Jacobian, and the discrete evolution shifts it adding two divisors corresponding to two different directions of the dynamics. So, and I can make one remark at this point that these formulas could be derived without any knowledge of Seiberg-Witten theory and so on, because it's a solution of the autonomous equation, which is written here. So we could find that there should be abelian maps of something, that period matrix should be a second derivative of, so there should be some period matrix, and but then only starting from the fact that this prepotential has a genus expansion, we could be able to get the Seiberg-Witten equations, combining this autonomous formula with the genus expansion. Okay. So for me, it's kind of it was kind of an explanation of the structure of the formulas in the non-autonomous case. By expand the.
Thank you very much.